Let's take a look at how we build and use the sampling distribution for the difference between sample means. So for this lesson, Mr. Peters and I both have containers of pennies in our classrooms, and we have used those this trimester to calculate sample means. We're going to use these containers as our populations for this example. So for Mr. Peters' container, he has 350 pennies in his population. It's skewed left. This is the mean for his container, and this is the true standard deviation for the entire population in his container. Here's my container. It has 518 pennies, has the same shape. It's skewed left. The true mean in my container is lower, and the standard deviation also happens to be lower. So let's consider a random sample of 32 pennies from Mr. Peters' container. So the distribution of the sample means that we could take using samples of size 32 can be described this way. This is something that we have already done. So I'm going to describe this as the sample mean, or x bar p, so that's for Peters. So there is a shape, a center, and a spread, and we know that these sample means will be approximately normal. We know that the real population mean is at the center, or the mean of all of the sample means. So the true mean for Mr. Peters' container is 1994.1. And to find the standard deviation of the sampling distribution, so we can pull this off of the formula sheet for the random variable, which is a sample mean. Here is the standard deviation. It is the standard deviation of the population divided by the square root of the sample size. So in Mr. Peters' container, the population standard deviation is 13.8, and we will divide by the square root of 32. So that is the way to calculate that standard deviation. We don't really need to simplify it at this point. Let's talk about the conditions that are required. Always, you need a random sample of pennies. Independence must apply in order for the standard deviation formula to be legitimate. So 10 times my sample size is 320, and that needs to be less than or equal to the number of pennies in Mr. Peters' container, and that's 350. So we know that the independence condition is met. And then notice 32 is considered a large sample. It's greater than or equal to 30. So what this means is the shape. This is about the shape, or this is the normality condition. The shape of the distribution of the sample mean is approximately normal. That word is really important. It is approximately normal, and that is true by the central limit theorem. The central limit theorem is about means, not proportions. So the central limit theorem says that no matter what the shape of the population is skewed left. No matter that shape, as long as the sample size is large, the shape for the sample means will look approximately normal the larger the sample gets. So let's also consider another random sample, but this time it's of size 40 and it's out of my container. So this sample means distribution, or this sampling distribution, is also approximately normal. The true mean from the population is 1989.3. And the population's standard deviation is 11.9. So that needs to be divided by the square root of the sample size. And again, the conditions are the same. So in terms of independence, 10 times 40, that's 400. That needs to be less than or equal to the number of the pennies in the container. And that's true, there are 518. So, and the normality condition is the same. So Notice 40 is a large sample that's greater than or equal to 30, so the shape is approximately normal. The shape of the distribution of, again, these are sample means for S from my container. The shape of that distribution is approximately normal. And that's by the central limit theorem again. So we know the distribution of means from Mr. Peters' container. We know the distribution of means from my container. So now we're going to look at combinations of those means. So here's our first example. A random sample of 32 pennies from Mr. Peters' container and an independent random sample of 40 pennies from Mr. Schaaf's container are selected. How likely is it that the sample mean from Mr. Peters' container is less than the sample mean from Mr. Schaaf's container? So what we're asking is, what is the probability that the sample mean from Mr. Peters' container is less than the sample mean from my container? So just like we did for proportions, rather than compare two random variables, we're going to combine these random variables in a way so that we can compare them to a constant. So we're going to subtract the mean of Schaaf, the sample mean from Schaaf's container, from both sides of this inequality. So on the right side of the inequality, we end up with a 0. And on the left side of the inequality, I have the sample mean from Mr. Peters minus the sample mean from Mr. Schaaf. This is the difference of two random variables. So we can find the shape and the center and the spread of this difference, and then we can use that to calculate the probability that that difference is less than 0. So to calculate that probability, we have to describe the shape and the center and the spread for the difference of two, in this case, sample means. That's what makes this a sampling distribution, because we are working with sample means. Those are sample statistics, and we already know that the sample mean from Peters and the sample mean from Schaaf, those are both approximately normal. Those are approximately normally distributed, but then look, this difference is just a linear combination. A linear combination of these random variables. So the shape of that difference, it has the same shape. A linear combination, adding random variables, subtracting random variables. Those linear combinations preserve the shape. So if I'm starting with two random variables that are already approximately normal, the difference is also approximately normal. So to find the center, the mean of the difference between the two sample proportions, all we need to do, means are easy to work with, is take the difference of the two means of the populations. So we already know those. So these are the means for the populations. Those are the means from the sampling distributions, the 1994.1 and the 1989.3. That difference will be the mean of the differences. This is what it looks like. I put a picture of what it looks like on the formula sheet. So notice, for two populations working with two sample means, the mean of the difference of those sample means, all we have to do is take the difference of the two population means. So we will do that now. So that was 1994.1. minus 1989.3. So our distribution has a center. The mean for the differences is 4.8. So we know the shape and the center, it's 4.8 years. So now we need to calculate the spread. So notice, this is just like when we worked with sample proportions. So we need to believe that the samples are independent of one another. And that's reasonable. These have to be two independent random samples. They're coming from completely different containers. They don't depend upon one another. So what we can do then is take their standard deviations. We can take the standard deviation from Mr. Peters' container, the standard deviation from Mr. Schaaf's container. So again, those are what we found on the first page. This is the standard deviation for Peters. This is the standard deviation for Schaaf. So we can take those two standard deviations, we can square them, and then add them, and then we can take the square root. So if we wanted to, we could find this standard deviation, we could find this standard deviation as decimal values. We could square them and add them and take the square root. The truth is, I'm just going to go ahead and use the formula from the AP formula sheet, and we're just going to go ahead and simplify this and do a little bit less work today. So if you take this standard deviation of the sampling distribution and square it, the population standard deviation is squared, but the square and the square root in the denominator are neutralized. So you end up with the square of the standard deviation from the population from Peters' container, so that's called the variance. That is divided then by the sample size that we are taking from Mr. Peters' container, and it's the same thing from my container. We end up having the square of the standard deviation of the population from my container. So squaring that creates a variance, and we're then dividing by the sample size from my container because the square and the square root, those undo one another. So the standard deviation from Mr. Peters' container, that was 1994.1. I apologize, that was the mean. The standard deviation from Mr. Peters' container is 13.8. The sample size that we are using from his container is 32. From my container, the standard deviation is 11.9, and the sample size that we are using is 40. So we can just simplify this, and we will have the standard deviation of our sampling distribution. So it takes a little longer for me to push the buttons on my calculator emulator here. I'm sorry about that. So I'm going to take the 13.8. I'm going to square that, and I'm going to divide that by 32. And then to that, I'm going to add the 11.9. And I need to square that, and we'll divide that by 40. So our standard deviation, I'm going to call it 3.08 years. All right, so now we have a shape, we have a center, we have a spread, and so now we can find our probability. So I want the probability that the difference, the mean from Peters' container minus the mean from Schaaf's container, when I'm looking at sample means, I want the likelihood that that difference is less than 0. Less than 0 would mean that the sample mean from my container was larger. Okay, well, let's change this to a probability in terms of z-scores. So we'll take our boundary of 0, we'll subtract the mean of 4.8, and then we'll divide by the standard deviation of 3.08, and that will give us a z-score. Let's find out what that is. So we will take 0 minus 4.8, so that's just negative 4.8. And we'll divide by the 3.08. So that gives us a z-score. I'll call it negative 1.56. So I'm going to say approximately because I rounded that. So this is the probability of a z-score that's less than negative 1.56. So I can use the normal CDF command in order to calculate that. So we'll go to second variables, and the normal CDF command will calculate this. So understand negative 10 is going to be the lower boundary. The negative 1.56 that we just found, that is the upper boundary. And we can highlight, paste, and we'll be good to go. So this probability is around 6%. I'm going to call it 0.059. So understand what's going on in terms of the picture. Again, I'm using the normal CDF command these days instead of using the shade norm command. You could certainly do that if you wanted to, but I would hope by now that we have a pretty good idea of what the picture looks like. If we're working with z-scores, the mean for z-scores is going to be 0. The standard deviation is going to be 1. My boundary is down here at negative 1.56, and I want to be less than that. I want to be below that. So that's the shaded area under the normal density function that represents our probability of about 6%. So this isn't a particularly likely outcome, but think about it. The mean of my penny container is around 1989. The mean from Mr. Peters' penny container is larger, 1994. What we're asking here is how likely is it that when we take sample means, how likely is it that the difference is negative? Well, what that would mean is that the sample mean from my container is larger, even though the real population mean in my penny container is smaller. So this is not an outcome that should happen too frequently, and it doesn't. So let's calculate just for the sake of practice. Let's try one more. So again, we'll keep the same sample sizes so we can use the same standard deviation. A random sample of 32 pennies from Mr. Peters' container and an independent random sample of 40 pennies from Mr. Schaaf's container are selected. How likely is it that the sample mean selected from Mr. Peters' container is at least 3 years higher than the sample mean from Mr. Schaaf's container? Well, I would expect this to be a more likely outcome because the population mean is larger in Mr. Peters' container. So how likely is it that the sample mean selected from Mr. Peters' container is at least 3 years higher than the sample mean from my container? Well, I would expect this to be a much more likely event. That's what we will see. But let's practice translating this into words. So how likely is it that the sample mean selected from Mr. Peters' container, here it is at least. So is at least, that's represented by greater than or equal to 3 years higher than the sample mean from Mr. Schaaf's container. This is how we take that statement and actually translate the English into a probability statement. This is the likelihood that the sample mean from Mr. Peters' container is at least, so is greater than or equal to 3 years higher than the sample mean from my container. So again, our sampling distribution, though, is about differences. So just like before, I need to subtract the sample mean of my container from both sides. So the probability statement that we're really going to work with here looks like this. It is an equivalent statement, but we're going to subtract the sample mean of Schaaf from both sides so that we're working with a difference of sample means. That's our goal. So the sample mean from Peters minus the sample mean from Schaaf, I am now interested in that being greater than or equal to 3. Well, no problem, guys. This is just a z-score calculation like before. So this would be the probability of a z, in this case, being greater than or equal to, our boundary is 3, and I want to subtract the mean. Our mean is, again, the same, 4.8 years. And I want to divide by the standard deviation because these are independent random samples from the same populations and using the same sample sizes. I can use the same standard deviation of 3.08. So, and now it's just a matter of making the z-score and calculating the probability. So this time we'll take the 3 minus 4.8. Well, I suppose I didn't need to do that. That's negative 1.8. Then I need to divide that by the standard deviation of 3.08. And that will give us our z-score. So the z-score is approximately, we'll call it negative 0.58. So since I rounded that, I'll use the approximately symbol here. So I'm interested in the probability of a z-score that's greater than or equal to negative 0.58. So what's interesting about this question, I'll draw the picture over here before we actually put it into the normal CDF command. So be a little bit careful with what the lower and the upper boundaries are. We're working with z-scores, so the mean is 0. The standard deviation is 1. My boundary is at negative 0.58, so we'll put the boundary right here. But I'm interested in being greater than or equal to that boundary. So in this question, the negative 0.58 is the lower boundary, and the upper boundary that we can use here, because we're using z-scores, an upper boundary of 10 is perfectly sufficient in the normal CDF command, and we'll basically be done. There's the normal CDF command. So the lower boundary is the negative 0.58. The upper boundary this time is 10. And this probability, like we suggested earlier, this probability is quite a bit higher. This will happen almost 3/4 of the time on average over time, so approximately that, it's 0.719. Again, that's our probability, and that probability is actually the area under the normal density function. So again, this lesson is all about working with the difference of sample means. And when you are working with the difference of sample means, this is the difference of two statistics. So statistics are describing samples. So this is a sampling distribution. And now we know how to find the shape when we're working with the difference between two sample means, and the center and the spread. Don't forget that the formulas in order to calculate the center, and I suppose more importantly how to calculate the spread, those are always available to you on the AP formula sheet.